So thanks everyone for coming out today. Stephen Lockwood is a senior engineer and partner with Hatfield and Dawson Consulting Engineers. He's got more than 35 years experience in the field of broadcasting and telecommunications engineering, a registered professional engineer in Washington, Alaska, and Wyoming, and a Bachelor of Science in Engineering and Engineering Physics from the Oklahoma Christian University. Hey, I got a great book that you might even have had something to do with. It just drives people crazy. Antenna physics, an introduction. I tell you, that is one hard. He puts just enough math in to make it confusing for me. Anyway, Stephen is also a senior member of the IEEE and the Broadcast Technology Society, and he's a member and past president of the Association of the Federal Communications Consulting Engineers. So with that, Stephen, thank you very much, and the floor is yours, and I assume Sean has set up sharing.
Let's see if we can figure out how to do this. I'll start the there. Now let's see. How do I do sharing here?
Hold on.
All right.
I gotta enable it here. I can find it. Okay, it should be good.
Okay. Let's see. Do I need to do anything, or you already got me shared?
No, you'll have to now select sharing and share whichever document you wish.
Okay, let's see if I can figure out how to do that. Now, let's see, that's in this screen here, and share. Oh, there we are, share screen, and I guess, there we go. And were we successful? There we go, all right.
And we have a nice big blue screen that says radio frequency safety.
All right. Well, I've been, it seems like inadvertently gotten so I was nominated as the person to talk about these kinds of things with the SBE, and we've done, a fair amount of this kind of work over the years, in that, our clients are concerned about radio frequency exposure issues and those kind of things along the way. My senior partner, Jim Hatfield, started nosing around in this world as our clients ask us about this, 40 years ago, and has been involved in all the standard setting and process of working through that. But as I travel the world and deal with the likes of us, I still find out that there's a great deal of misunderstanding about what is actually happening. The nice thing in both Canada and the U.S. is, as far as exposure issues, we've mostly worked through the exposure issues at some of the more egregious sites. Certainly in the West, where we have mountaintop sites and short antennas, those have largely been worked through, and most folks understand where the boundaries are, and as we've worked through what the FCC is required and what is Safety Code 6 is required as well. But I just wanted to run through the quick overview of what we're up to, and the mechanisms of radio frequency exposure, and looking at the biological effects, and then the science that has been there to help us understand what is there. And so I'm always amazed when people talk about what's happening, and they often get it wrong. And of course, a lot of it's in our group of folks is in jest, but making sure we all understand these things. I always like to start with this picture here. This is an AM station that was moved around the Port of Seattle, and we had one department of the port that decided they wanted to move the radio station. It was a 5 kilowatt AM station. They moved it down by this nice gantry crane, but then the licensee said, well, if we're moving, we might as well go to 50 kilowatts. And they quickly discovered that AM station pointing right at the gantry crane. The gantry crane made a lovely AM receiving antenna, and so we got this lovely arc at that. Now, so this really is not RF exposure as much of it is shock and burn from coming into contact with conductors that have radio frequency energy in them. This particular situation here, if you grabbed hold of that shackle good, you could hold it just right so you could hear the modulation in the arc. But the guy didn't realize, he learned quickly he didn't want to touch it with his hand because that hurt and smelled bad. And RF birds are unpleasant and make you say rude sailor words and hit your head on something sharp. And so the situation here was such that we have a clamp on current probe and put it around the guy's arm. It was an amp RF, and of course I took a turn with it as well because I'm that kind of guy. And we put the current probe on my arm, and I had about an amp of RF flowing as well. And my wrist did get a little warm as the day progressed, or as the time progressed, but I didn't stay too long. But anyway, we understand that certain aspects of this can be challenging and exciting, but the other thing that we want to make sure we understand is the difference between ionizing and non-ionizing electromagnetic radiation, and this is often a confusion amongst the general public. Most engineers understand this, but as we work through the spectrum, when we get up above visible light, above it's about 2/3 of the way through ultraviolet light, we get to a point where there's enough energy in the electromagnetic wave to actually physically ionize chemical bonds in our body, and that will break apart chemical compounds and physically change things. And this is the kind of damage that is done at nuclear reactors and situations like that. But in the radio world, which we're down in this area here, above power lines, so starting at 60 hertz in North America, and then up to 1 megahertz for AM, and then as we move up the band for television and cellular and microwave radio, all of those electromagnetic waves produce, if they're hot enough, can produce heating effects, but they cannot cause ionizing situations in your body and not break down chemical bonds. Let's see, why is there we go. So looking through this again on another kind of spectrum, as we increase in frequency, the wavelengths become shorter, and that's just kind of the take-home message of that. So ionizing, there's enough energy to break the molecular structure, and non-ionizing does not have enough energy to do so. There are in ionizing radiation, there's a cumulative effect. So over time, as you're exposed to non-ionizing radiation, the damage to your body increases over time, and that is something that they worry about. And so those are the dosimeter meters that folks who work in those industries carry around. For radio frequency, it is not a cumulative effect. It's generally a heating effect. And as your body heats up, it's assumed that your general thermal regulation that your body has can take care of the excess heat. So the exposure mechanisms, as your body is in an electromagnetic field, your body is a semiconductor load, and it has it's not a very good conductor, but yet it's still conductive. And as the current flows in your body, as it's induced from the antenna and the electromagnetic field, it can actually cause heating in your body. And it's much like a standard resistance electrical heater, whereas the current flows, the heating of that current can cause heating in your body, and it's based on the field intensity and how efficient your body is as an antenna. And so the more current, the more heat. And there's also a situation in low frequencies, so below, in the AM band and below, where you can have nerve stimulation at fairly low levels comparatively, and they can be painful, or at least you'll know that they're happening and you'll change your behavior. But as the currents increase, your temperature rises, and at certain levels of energy absorption, biological effects occur. And let me see, where's the cough button here? Well, I'm just going to back off and cough. Sorry about that. As the heating increases in your body, you can end up with flu-like symptoms and heat exhaustion, heat stroke, and a situation like that. And that takes a very, very large amount of radio frequency current flowing through you. And but energy below the thresholds that we've discovered are not significant and don't provide any continued damage. Excessive exposures above what the desired standards have created can create things like cataracts, and it's interesting to look at some of the research on that. There's a professor at Cornell who's done amazing amount of research looking at rabbit eyes, because rabbit eyes are very, very similar to human eyes, and so he can grow cataracts on rabbit eyes with microwave energy, and consistently doing that. But it takes an exposure that is much, much higher than the standards. And then also, the answer there is, if you've got a microwave situation, don't look into the waveguide with the transmitter on. And you're not going to be able to see RF anyway. And so don't do that. The exposure standards are based on a full body exposure, and there's situations where partial exposure can be higher. But there's also great deal of concern in some of the folklore about whether the standards really take care of the concerns for eyes and testes. Both of those organs do not have blood flow, so they're not good radiators. They don't have a heat sink attached to them, and if the exposure of RF is high on those two organs, they can cause damage. But those considerations are taken to an account into the standard and in all of the standards worldwide. And so, the best and safest approach and simplest approach is to stay below the standards. One of the other concerns that we often hear folks talk about is medical implants. And of course, my first caution here is I'm not a doctor, and I don't play one on TV even. And check with your physician. I've had a lot of friends who've had pacemakers and other devices like that, and often, there's concerns about that. I don't know how it is in Canada. I do remember some of this, in several trips to Alaska over the Alcan. That even in the 80s, there were signs on convenience stores that said, microwave and use, don't come in here if you have a pacemaker. And a lot of that is folklore, in that the pacemaker industry after pretty much the second generation of pacemakers kind of really worked through the electromagnetic compatibility issue. And the ones that are built today are really designed to be able to put your cell phone in your breast pocket and not kill the device. And so one of those things is to double check on that. And I know that there's other medical electronics that people are wearing now. And I think of some of the heart monitors and some of those kinds of things. So if you've got something like that, certainly check with the folks who are providing it for you. And then if you're with a large company and you're working around radio frequency energy, certainly let your company know. But the short answer is use caution and prudent avoidance. If you're concerned about this device, you probably ought not to be sticking your head in the transmitter while it's working, and those kinds of troubleshooting things. So as we continue our discussion of biological effects, the whole body heating is turned out to be the major concern of all of the take-home message of the research. And very low frequencies, we talked about that earlier, can cause shock and burn when you're touching situations where there's current flowing. That ends up being more of a situation where you're around an antenna, an AM situation like that crane, or you're touching metal on a building near an AM site. You can get situations where there's conductive energy in these devices, and that will cause trouble. And then of course, as someone who works on AM a lot, we make sure the station we're working on's off, and then we forget about the guy down the road. And my current RF burn happened a couple weeks ago, and that was exactly it. It was in the back of my hand. I didn't remember that the guy across the street was still on, and it hurt bad and made me say rude sailor words. Higher frequencies, above 2 gig, in like we talked about microwave, if there's situations where the exposure is really high, can cause some damage. But even a small energy, in a situation like that, where if you've got a small bit of energy but it's concentrated over a very small area, can cause a problem. But we just don't see ourselves in those situations, and most devices in that frequency range that we're dealing with are very low power, and so we don't have to worry about that. One of the things that often comes up in general discussions about this with folks around is they say, well, cell phones are new, and we've never, we're exposing people to things that they haven't been exposed to. We don't know what kind of problems are here. That's not really the case. We've had radio frequency devices for 100 years now, and we've basically been studying the effects of radio frequency energy on people for 100 years. And we understand that there are certain things that happen, but where the study started, really with the U.S. Department of Defense in the 1950s, where they were really concerned about all of the radar installations and all of the varying technicians that had to work around these high power radar sites, and then all the other high frequency situations, and then of course the broadcast facilities. And so there was a lot of research that was started at that time, and then more and more research, and there's just been thousands and thousands of studies on radio frequency exposure on various aspects of it, and there are three or two international bodies that have really looked at radio frequency exposures. There's two entities in the U.S., but the International Commission on Non-Ionizing Radiation Protection, ICNIRP, is one group that has looked at all of these studies and tried to come up with an exposure standard, or they have come up with an exposure standard. The other one is the IEEE, which is Institute of Electrical and Electronic Engineers, and they have a group of folks that are looking at the continued research, and my partner emeritus, Mr. Hatfield, has been on this committee, and I'm currently on this committee as well. But these two groups have looked at the research, and in the U.S. there's been a government agency, the National Council for Radiation Protection. They're generally more concerned about ionizing radiation, but they did form a committee for non-ionizing radiation, and to evaluate the levels that should be considered safe for for human exposure. Now, often when I'm in a public hearing for cell phone or broadcast facilities, we're trying to get it permitted. Folks will ask the question, why are a bunch of engineers coming up with what is essentially a health standard, and what do engineers know about that? And the answer is the engineers are coming up with that standard because it was their membership that was being exposed to radio frequency fields, and so that's the reason why the IEEE started this, and they started this in the 60s, and they've come up with that. Now the IEEE committee is open to, it's an open committee, so if any of you all are bored and want to go read research papers, it's open to anyone who wants to come. There are a number of engineers, there's a number of industry people, so most of the large companies, of like Motorola, manufacturers of devices, have people that come to these meetings. The various agencies. So I know that Industry Canada has some folks that come to these meetings, and there's people from all over the world. But there's industry people like consultants like us that go to these meetings. There's Department of Defense folks, and then there's some medical people, some epidemiologists, and various other folks that have come in that have an interest in this field that sit on these committees to come up with these standards. For looking at these standards and then moving those into safety rules for industry to abide by. In the United States, the FCC takes care of that situation, and in Canada you have Safety Code 6, which talks about radio frequency exposure and what limits are applied to that. And each one of these government agencies have come back and they've looked at the research and the standards that have been set up by these standard setting committees, and then also gone back and looked at the research themselves, and then come up and made it. And there's some situations where Safety Code 6 looks a lot like FCC, and other situations it looks a lot like ICNIRP, but there are remarkable similarities in this. Both sets of safety rules have areas for occupational exposure and the public exposure. The exposure standards, of course, everyone has to look at it, and in reviewing all of these research that has been done, and there's more research that's being done on a regular basis, for biological and statistical validity. So I, as an engineer, I have to look at the engineering side of that and say, have they taken appropriate measures to make sure that they know what power levels they're operating at, and they know what kind of are they controlling for frequency, and how are they managing those aspects of this, and then what levels are they working at? Are they working at levels? Are they doing their research at levels that are much higher than the standard? Well, that's kind of interesting work, but that doesn't really have any validity to coming back to setting a exposure standard. But we're looking for levels that unfavorable biological effects occur in humans. That's what we're looking for, and so as we look through the research, is it useful for setting a standard? And so. Two-tier standard, we talked about that. The take-home message of the research is coming back to a specific absorption rate where potentially deleterious health effects occur. So we're looking at a place where we know something happens to the human body. In all of the standard-setting organizations, they've gone back and looked at the research, and they've set that threshold, that specific absorption rate, at 4 watts per kilogram. That number comes out of studies that were done at Brooks Air Force Base in the 60s and 70s, and those studies were, they actually used airmen at the time, and actually put thermocouples in their bodies, and then had them heated in front of antenna systems, and the specific absorption rate of 4 watts per kilogram was determined that at that absorption rate is where the body temperature rises 1 degree C, and that was considered to be a place where we didn't want to go. Now, the question is that a bad thing? If your body temperature rises 1 degree C, is that something that is damaging to your body? And the answer is no. If you exercise vigorously or go outside on a hot day, it's not unusual for your body to raise 1 degree C. But that's a situation where 1 degree C rise in your body temperature is something your body can handle and work with. But that was where that threshold was set for exposure. Now, all of the standards have precautionary factors put in it. So for occupational exposure, in the IEEE standard and the NCRP standard all set the threshold at 1/10 of 4 watts per kilogram. So 0.4 watts per kilogram. And then for the public exposure is set at 1/50th of 4 watts per kilogram. And so we put in a safety factor in that coming up with the standard. One of the take-home messages, and I want to make sure everybody understands, is worldwide, if people obey the exposure standards that are out there, there's no injuries or adverse effects that we've been able to verify or see if you're obeying the standards. So live by the standards. The occupational versus general population, all of the standard setting bodies have allowed for higher exposure in occupational situations because they believe that occupational workers are aware of what an antenna looks like and where the higher fields would be, and are able to exercise control over their exposure. They understand where they are and how they're being exposed, and they can actually are capable to either go turn the transmitter to lower power or know that they don't need to stand in that situation. The public in both the U.S. and Canada, areas that exceed the public exposure standard have restricted access, and so I have not done extensive studies in Safety Code 6. I've certainly applied it a few times, but there's folks that are much more versed in dealing with that and how that affects your general operations. But the restriction of areas that are above the public exposure standard is key in all of the situations where radio frequency exposure might occur. One of the questions that I often get is, where can I go find more information about radio frequency exposure and effects on human beings? One of the resources that I've kind of been one of my go-to places is the Bioelectromagnetics Society, which is a research society that publishes a peer-reviewed journal, and I think they do that 6 times a year. Some years they do it monthly, and this is all of the research having to do with electromagnetic exposure to biological organisms, but they did a few years ago. They did a supplement 6, which was a review of all of the radio frequency exposure topics to that date. And so they actually they had a researcher write various chapters, and there's like a dozen chapters in there where they're looking at particular issues. So there's a chapter on cancer. There's a chapter on cognitive abilities. There's a chapter on issues of miscarriages and fertility. There's a chapter on the ocular effects and all of that. And so if you want to read more about it, now this one's getting a little, we've got, it's 20 years old now, and so it's getting to the point where it'd be nice if they would do that again and update it, but it's still a very, very useful tool. So if you go, look at, say, the chapter on cancer, they reference all of the papers on cancer, and there's hundreds of them that are listed in the bibliography, and the reviewer looks at all of these things and looks at all of the issues, and then comes up with a conclusion based on the reading of the science. And so what is interesting to me about that is, you look at cancer and they say, well, that, the predominance of the research shows that there's no effects of cancer. And we just can't find it. And, we're continuing to look. We're looking at, both the epidemiological issues with cancer, with all of those kinds of issues, exposure. And, the real problem with epidemiological studies is we never really can get a good handle on what the exposure is. So someone who, like me, who spent their youth sitting next to a big giant RCA transmitter shoveling coal in and was worried about the radio frequency exposure, I've no idea what the field levels were by that transmitter. I know at the time I thought, is this a good thing to be doing? I don't know. No one at that time, we didn't measure that. So there's also anyway, that's a good resource. The other resource is what the FCC's put out in Bulletin 56, and that's also a nice summary of biological effects as well. So if you need more information about that, and if you got any questions about that, Jim Hatfield and I are still looking at most of the research, and if you hear something, questions about that, something that comes up and says, and it's something that bubbles up in popular journalism, on sort of a, yearly basis, there'll be someone who's come up with a great study that shows something, and there's some issues with that. Usually there's some information about that available out there, from the other side. But, the exposure environments that we find ourselves in, of course, are, the broadcast facilities, the FM and TV situations, high power situations, can be an exposure problem. And then, of course, land mobile, public safety radios, and, the cellular industry, and those kinds of things can be in trouble as well. And then, medium wave as well. And for us broadcasters, the satellite news trucks and electronic news gathering trucks also can provide a particularly interesting situations as well. Most broadcast FM and TV in the U.S. and Canada are on high towers, towers that are several hundred feet tall, and generally exposure around the base of those towers is not an issue. We can calculate what those are, and certainly measure it as well. Where we end up with problems with broadcast FM and TV, and this is particularly the case in the mountainous West, is we've got tall mountains near big markets, and and they learned years ago that if I put a short tower on the tall mountain, it's unpleasant for my engineer to get to the top of that mountain in the snow, but it saves us a lot of money in the installation. We don't have to build as big a tower. And so we've got a lot of situations in the West where we've got, a 150-foot tower that is got pretty good set of FM antennas that have been piled on that over the years, and some analysis needs to be done at those sites to make sure that exposure is not an issue. Land mobile situations not particularly a problem. Most of the power levels in those situations are fairly low, and then we also have a low duty cycle. But we do end up with a real problem on rooftops, and this can be really exciting on some of the cellular installations where there are situations where people can walk right in front of those antennas and be in situations where their exposure is above the standard. So if you're in a situation where there's cellular antennas on rooftops, you need to make sure that some analysis has been done on those types of installations. And then AM radio and is typically even at 50 kilowatts. We've got fences directly around the base of those towers, and they're usually maybe 6-8 meters away from the base of the towers, and if you're not closer than that, you're not going to be in a situation where the exposure is above the limit. For satellite news trucks, we can be in a situation where we have power amplifiers of a kilowatt or more that are right on a rooftop of a vehicle, and those can be an exciting situation if you're up on the roof. But if you're off the roof, the manufacturers read the manufacturer's discussion on that, but don't get up on the roof when you're operating that facility, and that applies for electronic news gathering trucks. I've kind of laughed at that situation here in the U.S. because we largely don't use those vehicles much anymore. And I know in Seattle, I was looking at one of our facilities here, and they probably had $10 million of these news trucks out in the parking lot, and none of them have left the parking lot probably in 3 or 4 years because of all of our newsmongers are doing their reporting using bonded cellular channels, and they're not taking the trucks because they're a lot of trouble for those guys to use, and so they're not leaving home much. You can do the modeling for radio frequency exposure and in all of the services. The FCC has some nice resources on this, and if you're interested in finding out more about that, you certainly drop me a line and I can point you in the right direction. But the simple things you need to know are frequency, power, antenna height, and antenna location, and then if you're working with UHF and VHF antennas, you need to have some idea of what the antenna pattern looks like. But just remember, the farther away you are, the lower the signal gets. I'm still often amazed at people that still haven't quite got that situation in fully understanding that. But if you've got a several thousand watt facility that's on a tall tower, the farther you get away, your power decreases by the inverse of the square, so of the distance, and so it drops off very quickly. And this is another good example of that, where when you're close in and the balloon's small, you've got 1 watt. It's spread over that linear distance, and then as the balloon expands, as you get farther away from the transmitter site, that 1 watt spreads out over a much larger area. and so you end up with that situation. But for UHF and VHF modeling, back of the envelope, and I should have given you this in meters, since you all are educated people and know how to do meters, unlike us south of 49 degrees. Meters hurt our heads, but the simple.
I have a question, Stephen.
Yes, sir.
It's, if I read the left-hand side correctly, it's microwatts per square centimeter.
Yes.
But you get microwatts per square centimeter starting off with distance in feet squared.
Yes, that 360 is a magic multiplier that takes care of all of those sins of operating in the wrong measurement system, and so that solves that problem. But yeah, that cheats that situation. So it's a nice round number that is one that we remember. So that's why I always end up going back to this. But the metric version of this is 33.2 times the power in ERP divided by the distance in meters squared. And so it's but that's a simple calculation. If so say you're downtown on a tall building and you look over next door and that your FM station is 100 kilowatts ERP, and you can quickly calculate what the worst case would be in that building. If you net assumes that you're completely in the bore side of that antenna, that would give you a worst case, and that would also give you a worst case if you assume that your ERP was completely isotropic, and then it radiates that same energy in all directions. It gives you a quick worst case analysis where you can quickly determine whether this is even on the radar of anything I need to worry about. With UHF and VHF antennas, if you just assume you've got an antenna pattern that is squeezing that antenna, that energy into, a very small beam, and so in FM antennas and TV antennas, we've got a pancake-like pattern that's radiating from the radiation center of the antenna, and there's very little energy pointing down. So if we look at that, there's very little energy pointing down. This would be like a cellular antenna on top of that. And this also, in cellular antennas, those antennas also have, in the horizontal, they make a very, very tight pattern as well. So you've got this very tight pattern that's a lot like flood lamp, and we've all had enough experience with flood lamps where I've got a flood lamp above my garage, and it puts out enough light in my driveway that you can that is just really bright out there, but directly underneath that flood lamp there's hardly enough light to read, and so it's the very directional antenna. This is a typical FM antenna pattern. And you can see that, and this is in relative field, and this, I really ought to rotate this 90 degrees so that it's where we think about that. But that's in the main pattern, and as you go down from the antenna, so 10 degrees, there's a null that drops off, and 20 degrees, 30 degrees, and it drops off to a lower area. But you can see that at 70 degrees, there's a bump up in that field at that point. And if you calculate that, you can actually look at the real antenna pattern from the manufacturer, or I say real antenna pattern, what the manufacturer specifies the antenna pattern as, and then that would kind of give you an idea of what the worst case may be. One of the rules of thumb that I have used is just doing a worst case analysis. First using the real antenna patterns, the better choice, but for worst case, and not really sure, it's a safe assumption to say that there's a 10 dB power reduction in the antenna directly below. And then, if you look up and you say, hey, that's a FM antenna, am I being exposed? And you say, well, in this area, we can have 50 kilowatt FM stations. So let's do 10 dB reductions, 5 kilowatt reduction in that, and then throw that back into our far field equation, and that'll kind of give you a real quick back of the envelope calculation of what that power density on the ground could be. And then you also want to make sure that you're using that, a good distance to where that antenna is, and you have some idea what that is. For situations where you're in close-in antennas, and this is a rooftop situation, where you've got say a land mobile electronic remote pickup facility that you're using at 150 or something like that. Most people aren't even using those anymore; they're using their cell stuff. But if you had 150 megahertz antenna on your rooftop, the question is, do I need to worry about it? And as you get closer to that antenna, you're not really in the far field of that pattern. And so what you assume there is a cylindrical situation where you take that power of the transmitter, not the effective radiated power, but the power out of the transmitter, and you just spread that over a cylinder, and that kind of gives you a quick idea of what that power density could be. And that's a situation where that's a situation where you do want to keep your units proper in there. So if you're going to work in microwatts, you can start out in microwatts, and you don't have to do unit conversion, and then work in centimeters, and then life is better for you. Or you could do it the hard way and then try to come up with all the appropriate conversion factors. It's easier to do it from the beginning. So those are a couple of straight out tools that I use when people are concerned about hey, am I in a situation where things might be troublesome? And this is particularly the case as more and more cellular rooftops get installed around, and in situations where we're in multi-use buildings, and you've got a satellite receiving antenna on top of the roof, and you get up there and there's all sorts of other antennas and other situations on that rooftop, and you're not sure if the other users of the spectrum are doing their math appropriately. You certainly can go rent a meter and check it out, or call somebody like me to come up and measure it, or you can just quickly do a back of the envelope calculation and get some idea of what those limits are. One of the other situations that I'm running into a lot now, and it's just I talked about this in the beginning, the question of what are those of us who do spend a lot of time working in AM doing. One of the situations is we have lots and lots of construction near AM stations. So I'm running, with our longshoremen in the first slide there of arcing and sparking near AM stations. I'm running to that a dozen times a year now, and it's an exciting thing, because you always get called a little late in the process, and you got a lot of people that are very excited, and it's part of the business that I call consoling engineering. They're there, it's okay, and so we'll go down and pat people on the head and teach them not to touch the crane hook. And the simple answer is, don't touch the crane hook. Use synthetic slings, and if you have to touch the crane hook, you can use lineman's gloves with leather outers, and that'll give you enough insulation so you don't get shocks and burns. And the other problem that we've had around these situations is blanketing interference. So you're operating in 10 volts per meter, and you've got electronics in the crane that did not consider operating in such a high electromagnetic field. And so I don't know if you guys been into any cranes lately, but we used to have a plumb blob and a plumb bob, and an old crane operator operator with a calibrated butt, and he knew when he overloaded the crane, and that's what the instrumentation they use. But now they've turned it into a video game where you've got lots of instrumentation in there that are load sensors and boom angle indicators and all of these kinds of electronics that are, low voltage transducers that have a long cable running out to the end of the boom, and they pick up the AM station quite nicely, and they don't work. And one of the funny stories is we had one crane that its fuel gauge was troublesome because it looked like the VU meter at the AM station, and it was cute and we all laughed at it, but they had an interlock on the crane that when it got below a quarter of a tank, it shut off and said, go get fuel because you don't have enough fuel to play today. And so it kept shutting the crane off, and that became troublesome. So we taught them the joy of toroids and bypass capacitors. But in any case, those are some exciting situations. It's also humorous to those of us who've studied electromagnetics to watch folks try to solve this problem. And typically they start grounding everything, and in many cases that makes it worse because it makes the crane a more efficient antenna, and so there's some and then the other problem is I've shown up at construction sites where they've traded the shock hazard from the crane to a trip hazard because you look around the site and somebody's driven ground rods everywhere you turn, and so that's not particularly a good idea either. And so anyway, if you ever run into situations like that, we're happy to help you out, and this makes things exciting. The other issue that I've had a lot of problems with lately is we've had a lot of cellular workers. We've got a lot of folks that are using their towers that you had a broadcast tower and you have a cell company show up to put stuff on the tower, and these guys have never worked on broadcast facilities, and they bring their personal RF monitors, and they just don't work around broadcast facilities. They overpredict, and they alarm at any field, not just fields that are above exposure. And so, a typical example of this was a few weeks ago. I had a call from one of our clients, and the cellular company wanted the whole mountaintop to shut down all of the FM stations so that he could hang up a antenna on a 60 foot up a tower. And we were looking at it and go, well, all of these are 300-foot towers on this mountaintop, and there really shouldn't. We've measured it before, but there's no levels there that should be above the exposure standard. So we went down and measured on the tower 60 feet above the ground, and found out that the measurement showed that the radio frequency exposure there was 40% of the public exposure standard, but his personal monitoring device was telling it was 200% above the occupational standard. And so, this device lies. And there's a couple of reasons why. One of them is it's an unsuitable instrumentation setup for detecting multiple moderate level fields, and it adds different frequencies. So if you have two signals, it adds those signals incorrectly and comes up with an error every time it adds those situations. So if it's adding 12 broadcast facilities, FM signals that are all 5% of the standard, it's going to add all those incorrectly and come up with an error factor that's far above the truth of the matter. And so they're just wrong. And these are not measurement devices; they're alerting devices. And then the other problem I've had is folks tend to take those and stick them right up against the tower leg or right up against a transmission line and go, "Oh, we're in trouble." Well, you can't really take any of these devices that have a measurement type antenna and then bring it next to another conductor, because you desense that antenna and the two antennas couple. You're not measuring the field anymore. You're measuring the current flowing in the conducting material, and that current is coupling into the measurement antenna, and it's not a calibrated measurement. So, but in any case, I think that we've got to the point where I'm at the end of my hour, and but I'm I'm available for questions for as long as you need, and can help you through these things. Let me unshare my screen.
So, does anyone have any questions for Stephen?
Hey, Stephen, it's Wojtek here. Question for you. Up here in Canada, we have to prove compliance around guy anchors. What's your experience with guy anchor re-radiation at AM sites, FM sites, and what is expected in the U.S. to prove compliance?
That's often under or ignored in the U.S. Quite frankly, we have just depends on the situation and its geometry. So let's take the example of FM sites, and the FM sites can be an exciting time because what has happened in the U.S. is you have the original licensee who put up the 200 meter tower. And they've mounted their lovely antenna on the top of it, and they put in filostran in the aperture of that antenna, and then have done okay, and done nice workmanlike property. Well, then the second guy came along and put another antenna directly beneath that, but in his aperture he does not have filostran. And then the third guy did the same thing, and so you often see these stacked up FM antennas. And those other antennas are coupling into the guy wires and conducting down, and so you get right around the guy anchors, and you'll find that there are situations where the exposure around the guy anchors is elevated, and that can be an exciting time. Now, often I have found that folks are making a measurement mistake when they get in that situation, because they're running their meter closer than 20 centimeters to the conducting materials. But in general terms, in the U.S., I think it's a simple problem. I don't know what kind of fencing requirements you have in Canada, but the U.S. is not always very specific about their fencing. So, I've often just recommended folks go get just standard fence wire and T-stakes, and for $100 you can fence the areas around guy wires quite nice, or guy anchors quite nicely, and just enough to keep folks out of that situation. The other thing that we have found over the years is that you probably, just depending on your situation, you probably want to fence your guy anchors in any case. Especially if you're in the prairie states where you have bovine devices running around the field, and we don't want them to use guy anchors as recreational devices, and so fencing around those is not not a difficult or hard thing to do or expensive. With AM situations, I've not found this to be a difficult situation, because most of the time you've got enough breakups in the guy, with the insulators in the guy, that I have not shown that that's been a big issue. So.
I appreciate the answer. Maybe just one more follow-up. But the other thing that is written in the rules for the compliance for the Safety Code 6 GL08 reports is contact currents and induced currents. Although it is overlooked at this point by ISED, they may change that and make that a requirement. So do you have any experience with measuring contact currents at guy anchors, induced currents? I suppose my experience with induced currents is I haven't found one at an AM site or an FM site. Contact currents, I have measured them on guy wires and guy anchors, but it's one of those things that you got to move your finger around to find it. So out of 10 points, maybe I'll find one location.
Well, and that's the problem with contact currents is first of all, I'm a meter 65 and still a moderately fat man for that size. My impedance is going to be considerably different than my friend who's 6'4" and weighs the same as I am, and so the problem is the test subject is varies from person to person. I've done a lot of contact current measurements on HF sites and medium wave sites, and so what we have come up with is we have a human analog device that we've gone back and looked at the research, and there's what the researchers call the generic human impedance, and so we made a device that way with a capacitor and a big resistor that allows us to make measurements. And this is we use it around cranes, so we've made it beefy enough that we can have several amps flowing through it and not burn it up. Which we version A and B had that problem. Version C is much better. But when you use this device, you've got a standard measurement device, and it's got a copper plate at the bottom that's roughly the area of two number 11 shoes in the United States, and so that kind of helps us have some standardization there. The problem, I have a contact current meter that, like I used on the crane there, that you snap around. It's a toroidal current transformer that you can snap around your arm or leg, and then you reach out and touch that. Now the problem is the contact current limit for IEEE. The U.S. doesn't have a contact current limit in the FCC rules, but in the contact current limit for the U.S. or for the IEEE is now lowered to 40 milliamps, and my meter goes to 1 amp, and so and the problem is I'm the test subject, or you are. If I come to your site, you're the test subject, and you put that current probe around your hand and reach out and grab the crane hook or the side of the building or the upright support, and now you're exposed above the standard, and what I've discovered is now is my threshold of perception when I'm around medium wave and HF is I don't feel anything till I get to 250 milliamps. So I'm, well above the standards at that point. And now, I think a lot of that would be because I've been accused of being insensitive, and my loved ones accuse me of being insensitive all the time. And so I, and I don't feel that. Now I've had up to 1.5 amps flowing through me at some HF sites. And the nice thing about that is it's flowing, if you got a good surface area and you've got that current density low enough, you don't get the RF burn. But because of the skin effect, it flows on the outside of your body and doesn't stop your heart muscle. 100 milliamps will stop your heart muscle at 60 hertz. And so, but we don't want to do this. This is kind of, more of the hold my beer and watch this kind of moment. Don't do that. But so going back to the device that we've made to measure contact current, that's the better device. There is no commercially available repeatable device. I can certainly send you, if you need to make these device like this, I can send you what I've done. But it is something that we've used, at sites for cranes, that, we had a situation where we couldn't put in insulated slings, and we had to use steel slings to support this because it was a tilt-up concrete building, and the slings had to go through a block. And so we had a situation where we had to have the guys actually touching the crane hook, and so in that situation, we went out out and measured when they moved the crane around and said, hey, this is, 300 milliamps today. So, put your gloves on and then we would put the gloves on and then use the clamp on current probe to make sure that we were getting enough insulation when they touched had to operate the devices or touch the crane hook. But yes, it is indeed a problem. Of course, I don't think there's much HF around anymore since Sackville went away. May it rest in pieces. And one of the things I found around at HF sites is that the open wire transmission lines, the vertical supports underneath those will have available currents that will make you stand up straight and stop mumbling. And in any case, so.
Thank you. I greatly appreciate that. That's very insightful. Thank you.
Certainly.
Do we have any other questions?
Sure, Harry. I have a question, or maybe it's an observation that you can help confirm for me. But on your last screen there about personal monitors, you mentioned don't use around AM stations and unsuitable for multiple high broadcast fields. I have a co-located site. There's an AM, got 3 towers, and I've got AM on anywhere from 2 to 3 of them, and I've got FM on the tall center one. I've had problems with climbers telling me that their alarms are going off even when I wouldn't expect that to be the case. But I'm wondering if this combination of FM and AM can create these kind of
the first thing to do is to take their monitor and roll it over and look at what frequency range it operates at. And you'll find that it starts at 50 megahertz. We're operating at 1 megahertz with the AM. And so you're using this device outside of its designed frequency response. And it's going to lie to you every time. And it's funny, I had a situation where it was a 50-watt NDB, non-directional beacon, operating at I was like 300 kilohertz or so, and putting out a Morse code group, and they were putting a cellular facility on that tower, and the guys were just screaming, said, we're getting exposed. And I go, it's 50 watts. Really, you can't. There's no situation where you can be a problem. So I went out there, and the first thing I saw was, turned over those meters, and it says 50 megahertz, low end. And so, it's leave it in the truck. It's not the right device to be using here.
I guess I might have thought that if I was operating like my AM operates at 1.29 megahertz, if the meter's not working until 50 megahertz, that it would be less sensitive.
You would think that,
but that's not the way it works.
That's not the case, and
okay.
Because you'd think, well, I have this very, very long wavelength, and compared to the little tiny antenna in this device, but the problem is that's an active antenna in there that's going through some filtering and some sampling, and so who knows what they did down in that low end. And how they've taken care of it. And, one of the cheaper of these devices that you'll see now is FieldSense. And it's 3 dB cheaper than the NARDA meter. And so, you can get them for like $600. And if you look at them, they're real proud about selling those. And they say, hey, you only need one worldwide. It does Safety Code 6, it does FCC, it does ICNIRP. You don't have to buy multiple meters. And if you bought the NARDA meter, you'd have to buy 3 meters that were calibrated this. Well, you look at how they did that and what they did. And so if you look across the spectrum, each one of these standards has, they're remarkably similar levels, but there's different areas where the curves bend at different times to for varying reasons, but they vary, up to 6 dB difference in some of these areas, but the standards are remarkably similar. But now you take this measurement device and we've drawn a line in it. Well, you look at their measurement device and their specifications, they got a nice specifications chart on it, and it's plus or minus 6 dB. And so they made a fat curve, hit the bottom of everybody's standard. And so it's going to alarm before it should, in order to meet I only need one worldwide. And so then you take that, the multiple frequency problem and the AM problem, it's just ends up being a real troublesome issue. Now they're using diode detection, and there's 2 regions of diode detection where if you use a linear detection or a square law detection, you need to be in the square law region of the diode. And if you're using the linear detection, instead of adding the signals where you get A squared plus B squared is going to give you the total field. What you end up with is A squared plus B squared plus 2AC. Now you say for 2 signals, that 2AC is not a big issue. But if I've got a dozen signals coming in that are all 5% of the standard, that error ends up being larger, much larger than any one component. So that error gives them. So if you're operating in a place where you're an elevated field, but you're not above the standard, if you bring that device in, it's going to scream and lie to you and say you're 200% of the standard. You're going to be above the limit. And so really, what those devices are alerting devices. They're to tell you that there is an electromagnetic field present. They are not a measurement device. So the little lights on the side that say, 20, 40, 60% are not, they're not measurements. All of the measurements worldwide are a spatially averaged full body measurement. And these are a point source. And so that's not an appropriate measurement method. But they are useful to tell you that the transmitter's on. But other than that, leave them in the truck or your broadcast sites.
You had another little point on there that would have been helpful for me about a half a year ago. I had a guy on the tower, and he's a young guy. And the thing is, these meters are new to them, and they don't know how to use them properly either. Because, he's showing me that when he touched the meter to the tower, that it was going ballistic on him and yelling at him to get off the tower.
Yeah.
And I said, well, I managed to convince him that I have had people climb this tower for the past 20 years at these particular settings, and things were fine. But, and when he held the meter, a few inches away from the tower, things were okay. And I know from working in the past at the guy anchors, we were sent out a meter to measure some of the fields around our guy anchors. And it can make a difference if you're on 6 inches on the left side versus on the right side, what your meter readings are of the guy wires. But if you touch the guy wire, it's just insanely different.
Yeah, and that's just the the decoupling of the antenna to the steel, and and all bets are off. And the IEEE standard, there's a IEEE standard on measurements, and they have a great discussion of this about and they say 20 centimeters. And that's where it is. And so but the problem is people think, well that just means there's current flowing, high level of current flowing in the device or in the steel. And no, is what's happening is you're decoupling both you're decoupling the measurement antenna when you get too close. So
thanks.
Yeah.
Anyone else have any questions? Well, while you guys are thinking of questions, I'll say thank you to Stephen for a fascinating presentation. I'll also tell you that Sean here is a web genius. He's already got the first 2 weeks set up as video buttons on the web page, and I'm assuming that by the time we all say goodbye, the third week will probably be up or shortly thereafter. So
I'm shooting for this weekend. We'll have it up, and we'd like to thank Jason Sharp for hosting the web space for these files. And when you click on them, you can rewatch them. Write down any links that are referenced or any products that are referenced, and if you wanted to, like if you click on it, it starts playing automatically, but you want to download it so that it's local on your machine, you just got to go File, Save As, and then save the MP4 file onto your hard drive, and then you can watch it at your leisure later on.
all right. So
Well, thank you so much for your kind attention and the invite. And if you have any questions along the way or anything, feel free to drop an email or give a call. And we will condescend to cross 49 degrees if they ever let us again. And and I always tease people. I say we limit our practice to this planet, but we do what we can. So.
well, I guess you're not going to get any calls to the space station then.
Yeah, not yet, but we'll have to reevaluate our policies if the offer comes.
Well, thank you very much, Stephen. I will mention that we do have an annual general meeting coming along soon, which we'd probably like to pair with another presentation. So if you guys can think of a topic, please send us an email, let us know, and we'd be happy to oblige.
Okay, well, and if there's anything you think that we can help you out with, or any questions or education that can help out, happy to work through that as well. So, certainly enjoyed the time. Thank you.
Well, thank you very much. It was very enlightening. So much appreciated.
Thanks.
All right. And I guess with that, we'll say goodbye, everyone, and talk to you soon at the AGM. Take care, all.
Thanks for coming.